Hello community! Let's talk about the latest technology in video AI generation when we build three-dimensional worlds with our AI. But we have one major problem. Our vector spaces are dead spaces. Nothing moves at all. Because our AI vector spaces are static, devoid of any motion or any dynamic properties like a velocity. So, vectors in our AI spaces, in our models, are just static pointers. They are not dynamic or moving entities. And this is explained because there's a difference in mathematics and the physical definition. So let's change this. At first we change that we take now images with 360 degrees. So we map here a three-dimensional world onto a two-dimensional surface. This is great. And then we have the idea, then we generate here with AI our three-dimensional worlds, and we send off agent to explore this three-dimensional world. And the moment we move to video, we do have temporal reasoning in our AI system. And therefore, we have dynamics in our AI system, because if there's a particular job to be done by multi-agents that coordinate their actions, we need temporal reasoning, and we need this generated in our GenAI videos. Now, you might say, is it technological available? Yes, look, this is all we need. And a little bit of an AI. But what AI in particular? So the first step is clear, no? We train a vision language model on a text to a 360-degree image, and these are our pairs, text and image pairs that we know. And then we use here our beautiful things like VEO2 from Google to generate AI video sequences. You see what we've done? We moved from a dead space where there's nothing at all, just dead images that do not move at all, and suddenly we integrate motion of our objects, of our environment, and we have video sequences. Now, the moment we enable agent now in our videos, and our agents explore now and reason, because they work together, about their virtual 3D environments that might be perfect copies of the real world, and we encounter a problem, partially observable real-world spaces and virtual spaces. So no problem, we have AI, we just rebuilt those missing spaces. So the challenge is now to build a dynamic, explorable 3D environment from a minimal input. Let's say we have, like I showed you, only a single static image, but a 360-degree image of a city. And then we send off our agents. And we have to make sure that we allow our agents to imagine unseen parts of the environment as they navigate the world. Because as you see in the image, they are corners. We don't have recorded yet. So those agents running around in our 3D environment, they have virtually to generate unseen parts of the world. So they have here to look behind the corner. But since we're in a video, we have restriction. We have to ensure a spatial consistency and a spatial coherence during this exploration, even for a long sequence of actions. It cannot be that suddenly the facade changes or the houses changes, the style changes. It must all be in a coherent flow. And then imagine if two different agents suddenly meet and they constructed their world. And now, if we have multi-agent reasoning, the agent predict and simulate each other perspectives. Yes, of course, because if two agents meet in their constructed world, they must be at least similar, no? So we can bring them together and then recalculate their paths. So this sounds interesting. So let's do this. So we pre-train a transformer on a simple task. At first we have a text to an image, but now we go with a text to a 360-degree image, so we describe exactly what we have here. Or, as shown, we take a single flat image and we train here our transformer architecture that it can now construct a 360-degree two-dimensional image of the 3D world. So this is a standard procedure that we know how to do. It is interesting that we have the mathematical formulas, but we have not applied it yet. And you might say, why? And I don't know. And I was fascinated when I read this research by Johns Hopkins University. But you know what? It's all in the pre-training data. The quality of the data, we always come back to the same. So imagine we have 144 images, our now 360-degree images of a particular part. Let's say it's a park in a city. And then we start. So I say, hey, a park in Paris. And now the AI exactly knows, okay, those are my images of a park in Paris because I have the metadata, I have here the verbal description. Then I go on and say, where children play. And okay, so we have here now, those are all here the training examples. My AI knows here from the pre-training data, those are all possible examples that it could generate a video of. And then I said late in the afternoon. And then AI selects exactly, those are now my training data set. This is a park in Paris where children play late in the afternoon. And this is here my input data I can generate a video of. So you see, this is really interesting how we build here the video generators based on the training data available. And when we use here the fusion of different video elements. Let's do this in real time. Let's say I'm here in my 360-degree still image. And I make now here an AI system and I say, okay, just move on. Just walk down the street. Now you see, suddenly we have a dynamic element. We have no dynamic element until now in AI. Because now I have a vector velocity moving now into the image, into the whatever we have to construct in the video sequence. And now imagine at the same time I have another agent. And the other agent goes down this street. And somewhere behind there, they will possibly meet. So neither of them knows exactly what's behind those buildings. So this agent moving forward will build by AI, by generative AI, the environment. It has to be similar, it has to be coherent, the style has to be the same, and this agent with a certain impulse moves on. And this agent moves on and they meet here somewhere behind, and then their world, their constructed world, has to be almost identical. So this is now in AI video generation. This is a new challenge, but an interesting one. But let's make it easy. Let's think, hey, we have an idea that we copy here the complete Google view, of the streets of your city. You have a little small city and you have, I don't know, on Google available some 1,000 images. And then you have a complete visual set for your agents to move and explore freely. Which is great, but this is no challenge, no? Imagine if you only have 20% visuals of your city. Complete streets are missing. But then our AI agents now, moving freely or doing some task, having a challenge, our AI agents will have to generate here a coherent visual continuation. And since our AI agents have now a velocity, they are now dynamic in our virtual three-dimensional world. They have now to generate here their environment as they move. And let's say either you go with SORA by OpenAI or you go with VEO2 that can generate 4K videos, which is really nice, by Google. Let's say we go with Google. Have a look at Google DeepMind's VEO2, the new state-of-the-art video generation model. This is all artificially generated. This is not real, whatever you see. This is simply unbelievable, and you can generate this in 4K video. I am blown away. And here you have, always down here, you have here the prompt. Have a look here at this artificial video. It almost looks real, but you understand the physics is not there yet. But as you can see here, this is our prompt. And you have to define absolutely what you want here for this video generation. But if you look closely at the tires, how they have contact with the surface, you see physics is missing. So the training data are there. You know exactly how to generate the car drifting along the background is there perfectly. We can have 4K resolution. But what we are missing still, although we have this beautiful prompt, and I'm absolutely impressed with this, the pure physics, as a human, that this is not really the behavior of a car drifting here on the tarmac. So what's missing is physics, but otherwise here, if you look at this is already getting quite close to reality. Or look at this example. Look in the mirror. Can you see here? Unbelievable. There are real people. There's motion in those people. Look at the details that is there. And you would assume that this is a calculation after light reflection in the mirror. But no, it is not. It does not include physics yet. Although with this training data set, this AI is real excellence in generating this particular scene. And as always, you see here the complete prompt. You define what you want to see. And here in our case, Google VEO2 generates here this image sequence. And I have to tell you, it is the best I have seen up until now. But it is still missing the physics engine. So let's go on with theory. So you see, the physics behind all of this is simple, no? We have here an equirectangular panoramic images. Even if we have here original panoramic image and then we say, hey, I just need to rotate this, we have some simple mathematical formulas and we can calculate here immediately a rotated 380 degrees. So we have no problem here with a grid coordinate system and spherical polar coordinate system. They are just functions transforming one to each other. And if we go here in different other systems, we have no problem at all to calculate here rotational transformation in spherical polar coordinate systems. They are simple transformation. Now, the AI model itself can be much more interesting. And here, reading the publication here by Johns Hopkins University, I'm going to show you in a minute, they had exactly this idea with they built their diffuser backbone here with a rational autoencoder and then the classical diffusion model. But they have here a speciality, because if we are working here in multiple coordinate system and generating multiple view of this same scenery, we have to make sure that there is a spherical consistent learning methodology. It must look the same from all the different angles. If we have three agents and they meet, they come together on one place, in one park, they meet, all their constructed views must be identical whenever they see the other agent in their, let's say, video. So therefore, there is this spherical transformation here, real nice, to make sure all the training data here come together and we have a spherical, consistent learning algorithm. They also went on and said, hey, imagine if I have one agent, this is simple, no? One agent has a certain field of view, and this is whatever we can generate from this one agent. But if we have now multi-agent scenario, this is now interesting. Imagine, we have here a pedestrian crossing the street here, and this pedestrian is moving along with a certain velocity. Now we have here our bus, and our bus blocks here the view of this approaching car. Let's say this car is agent 2, our pedestrian is agent 3, and the bus here is our LLM agent 1, calculated by this example here with an OpenAI LLM. Now, the AI in the car might notice here, if it's here, there's a pedestrian walking here, great. But unfortunately, with current systems, we do encounter here a problem, because what we do not understand is when the car comes closer and the view is blocked, that the AI system is not able to understand the physical world. That it understands if there's an object with a certain velocity and it's moving across the street and the view is blocked, there is a potential danger of a collision. So the intelligence currently of this AI is not high enough to understand the physics of this scene. It is just analyzing here dead vector spaces. And we have to change this. We do have to change this. because the equation of linear motion in physics are known. Come on. But still, our AI will fail since the training data did not include at all anything about physics. So this is not acceptable for an AI, because you know what? Even we have the input as our panorama image, we can calculate here the depth map. So we do have the three-dimensional depth distance of an image. From a single flat image, we can do this. I have multiple videos on this. This is simple. So therefore, we do have here the complete, if you want, three-dimensional information from a single image. We can calculate this. And why won't we start to include now physics in our real 3D distance correlated generative AI world? You know what we can do? We can do amazing things. As shown here, we have here the real input view. And if we try to calculate now this in our generative AI video sequences, you know, this is almost the same. Or look here, the street view, this is the real street view. And if we then continue to move along on a specific vector, on a velocity, and we walk in this direction, so you see this corner becomes now this corner, we can generate these videos, no problem at all. And you know what else? We can have here a 360-degree image, and we have simple transformation. We can now generate flat two-dimensional images for each perspective. Look, we have here, standing here right next to this, whatever this is, a church or whatever, or under the tree. We have so many flat two-dimensional perspective just calculated here from this particular image. So the information about our space is there. Now the next step is just to make it really dynamic. And here is this beautiful publication, and this is here by Hopkins University, and you see here the authors. This version I'm referring here is to mid-November 2024, Generative World Explorer. They also have a beautiful homepage. Have a look there, Hopkins University. And they just published here a brand new publication here, December 12, 2024, Hopkins University GenEx, generating an explorable world. It was before our video systems were published here, and they built their own system. But I think if we use here the power of OpenAI or Google here for this world exploration, if we can build this in 4K resolution, this is simply gonna be amazing, because look at this. What they already say, hey, if I move here a specific path, and you see they already have here the vector in place, maybe just indicating here a change in the location. And I have here at this point in time, in space, those images that show me the surrounding. And then I move a little bit further, and then I have here the sum of all of those images. And then I move further, and then I have here the sum of all of those images. It is so easy to generate now a video moving along with a certain velocity beautifully. And if we now build our generative AI worlds, we have all the data, but we need a lot of computer infrastructure. No discussion about this. But the technology to do this, we have it. Look here, what I like is just this geometric 3D vision made easy here. Those are the authors, beautiful. They have here from December 2024, and they show us exactly how it is done. So we have, that stands for dense and unconstrained stereo 3D reconstruction of an arbitrary image, a flat 2D image collection. We can build our 3D worlds with a precision that is just amazing. So we have our video generators for AI. We have all the mathematical formulas to describe motion, to describe the physics, to describe rotation. We have here all the ways to calculate here, even from single flat images, three-dimensional worlds. So there's nothing holding us back, going now the next step and hopefully integrate now physics into this. Because imagine, just imagine, we have here a single image. There are some buildings and there's here an open street. And now let's say we have two different tasks. Either we say, we fly a drone now down this road, no? And this drone flying here down, and here you have the 3D point cloud, it's taking images. So it is really recording the real world and building here in real time here the real, if you want, world in the virtual AI calculation. So whenever then a pedestrian comes along, we have here the perfect, identical, coherent generative AI environment. Or you say, hey, I just imagine and I calculate I would fly here a virtual drone down the road, and then the system starts to calculate based on the training data that it has, and hopefully the training data show here have data on a similar city, on a similar architecture, on a similar daylight or nighttime recording or whatever. So we can build then in a virtual world the dynamic of a virtual drone that would fly here and build a generative AI world just out of the AI system. And then we could, if we go there, we just can compare it and optimize it. So possibilities are simply amazing. So we can have here an active three-dimensional mapping from a single image if we include now motion, if we include dynamics in our AI videos. And the authors here, and I would like to state here the very last sentence that they say here from Johns Hopkins University, they say this work marks here an advancement toward a real-world navigation, or if you want, interactive gaming. Why not game in your own city, in your local district, and achieving here human-like intelligence in embodied AI. Yeah, imagine if we would have here a robot moving around, and the robot would know exactly every time that it makes a movement of the environment and what will be the changes induced by the movement or by an action of a robot in this environment. At first, we can calculate it here in a three-dimensional virtual world, analyze the outcomes, and then optimize here the real-world interaction of robotics systems with embodied AIs. And you know, all we have to do, we simply have to integrate physics in the next step, in the next evolution of AI. I hope you enjoyed it a little bit. It would be great if you would become a subscriber, and I would see you in my next video.